Okay, hello everyone. So I wanted to share with you some of the hints and solutions to the week 5 problems on permutation groups and isomorphisms. And this is a really important section. You're going to see why when you do your exploration projects. And one of the key things to keep in mind here is always know for both permutation groups and isomorphisms what type of object you are working with, and choose an appropriate representation or object before you launch it. So do some thinking ahead of time before launching it. And so a prime example of that is in the first question. So you're asked to write down types of disjoint cycles that are possible in 5 elements, and then to classify them as even or odd and compute orders. So to classify them as even or odd, you'll want to keep them in disjoint cycle form, because in a disjoint cycle form, you can see the order by taking the least common multiple of the lengths of the disjoint cycles. But to compute or to see whether they're even or odd, you'll want to write them as a product of 2 cycles, and then see if the number of 2 cycles is even or odd. So by choosing the correct representation and working with the correct representation, this problem won't be too bad. And then in part B, there are questions in the textbook that are just like this. So you can follow that model. In question number 2, we have permutations in S5 that fix 1 and 3. So the way that I would think of this subgroup is permutations that only switch around the remaining elements, which are 2, 4, and 5. So since 1 and 3 are fixed, only 2, 4, and 5 are like swapped around or could potentially be swapped around. This is really a subgroup that is going to be isomorphic or the same as S3. We can forget about 1 and 3. They've already been taken care of. They are already staying the same. Yeah. So once you have that idea in your head, you kind of know everything you need to know about H, or you can find it. And then the same idea goes when S5 is replaced by Sn. And when you're thinking about An, the main thing that you need to keep in mind is that An has half as many elements as Sn. Okay. In number 3, we're thinking about writing groups as subgroups of symmetry groups. So the method that was described just uses the Cayley table. In this, we are going to use the fact that we know that these are symmetry groups of particular objects. So for example, we can label the corners of a square or a rectangle and keep track of where they go. So this is just like when we were initially dealing with symmetry groups. We labeled corners to keep track of the symmetries, not because they determined whether there was a symmetry or not, but to keep track of where the symmetries were going. And so, for example, you could now record a symmetry not as this is the visual placement of, like, I see a 2, a 3, a 4, and a 5, or something like that, or 2, 3, 4, and 1, more likely. But that you see that where there was once a 1, there is now a 2, and where there was once a 2, there is now a 3, and where there was once a 3, there is now a 4, and where there was once a 4, there is now a 1. So that might be an example of the type of result. So describing it like that is much more like a permutation description because you're replacing a 1 with a 2 with a 3 with a 4, and a 4 with a 1. Okay. And so that's the type of description that 3 is going to be getting at. This is not necessarily going to be the same subgroup that was found in the video. It's all going to depend on how you label your corners. And I don't, yeah. So, and I don't actually remember if it happens to be the same one. So in number 4, you can use the same technique. You can label an object and look at the permutations of the corners. You could also use the more general idea that, and that's the one of looking at a Cayley table and seeing what sort of permutations you have on the elements in each row, and using the permutations on the elements of each row to define your isomorphism. Okay, to show that the set of even permutations is a subgroup of Sn is not very challenging. I think that the most challenging part, well, first of all, you have to write these permutations down in the right way. And we know that every permutation can be written as a product of 2 cycles. So write down your permutations as products of 2 cycles, because that's what's advantageous when we're dealing with even versus odd. So if you write them down like that, you can you'll have a good start, and you can pretty much automatically see closure. And then the inverse will probably fall on your lap as well, to write the inverse of a product of 2 cycles. Again, is not too bad. Okay, I think that's all I'll say about that. Is the set of odd permutations a subgroup? Well, there's a reason we don't talk about it. It's not a subgroup, and the reason is that we're missing the identity, of course. Okay, number 6 is just like another one previously. I don't know why I repeated that one, so apologies for that. Okay, number 7, what are the possible orders for elements in A4? And then why does this imply that the center only consists of the identity? So this is kind of like writing out the possible forms of elements in S4, except we just have to eliminate the ones that are going to be odd. So we know that any 4 cycle is odd. And we know that a 2 cycle alone is odd, but a 2 cycle times another 2 cycle is even. Okay, so we can have elements of order 2, and we can have elements of order, well, I guess the next question is, can we have elements of order 3? So we can in fact have elements of order 3, and that's because a 3 cycle can be written as a product of 2 cycles. So a 3 cycle is even as well. Now, can we have a element of order 6? Well, it turns out that we cannot have an element of order 6, because we would have to have a 2 cycle times a 3 cycle that are disjoint. And of course, A4 doesn't have enough elements. There's only 4 things. 4 things can't fill 5 slots. So we can only have elements of orders 1, 2, and 3. So why does this imply that the center only contains the identity? Well, this is actually a little bit I don't know, more challenging than the innocent question implies, because there are a lot of different ways that you could go here. And I think that that's one of the big challenges of group theory, is when you start to collect all of these facts, sometimes you're like, well, there's so many different possibilities or things that I could go. So I hope that if you attempt this question, you try many, many things. So you should attempt a proof by contradiction here, I think. And, or at least that's the way that I did this one. So assume that you have more than just the identity in the center. So if you do, that means that you will have an element of order 2 or an element of order 3. So take those two cases separately. So assume that you have an element of order 2 in the center. Well, that means then that you're going to have, let's call that element alpha. So an element of order 2, alpha, is in the center. If that element is in the center, that means it commutes with everything. So let's take any element in the group of order 3. Let's say it's beta. Okay. So we have alpha, an element of order 2 that commutes with everything, and beta, some element of order 3. Multiply those guys together. That product, alpha times beta. Well, since alpha beta is equal to beta alpha, those two things commute, the order of that element has to be equal to the LCM of 2 and 3, which is 6. So alpha beta has to have order 6. But that's a contradiction because we know that there's only elements of orders 1, 2, and 3. And you can do the same thing for the other elements in this group as well. Or sorry, for the other cases. So assuming that you have something in the center of order 3. Okay, so that one's a little tricky, or quite a bit tricky. Just because of the number of directions. The actual proof doesn't turn out to be too bad, but finding the right little nook and cranny, finding the right cranny to look in, it's difficult. Okay, so in question number 8, if you have, you're defining a subgroup H based on whether two isomorphisms send two elements to the same thing. The key thing here is to keep in mind what kind of elements H has in it. So H has elements of G in it. H does not have maps in it. It does not have images of maps in it. It has elements of G in it. And that's going to be your key fact, the key thing to keep in mind. So you could use the one-step subgroup test. You could use the two-step subgroup test. I think either one will work. You could even, again, go back to the properties of subgroups, I should say. In question number 9, we want to show an isomorphism. So in order to show that two things are isomorphic, we actually have to show an explicit isomorphism. So show a map between G and H, and then show that it's 1-to-1 onto and operation preserving in a way that sends the identity to the identity. Okay, so you need to show 1-to-1 onto, preserves the operation, and sends the identity to the identity. Okay. The operation preserving bit, very, very, very important for group theory. It's what makes a group theory map a group theory map. It's the thing for group theory. Okay, so show that. Yeah, and that's exactly what C is asking. Is it operation preserving under multiplication as well as addition? And then in number 10, you want to look at Group Explorer and see if these two groups are isomorphic. And remember, for two groups to be isomorphic, they should really have the same Cayley table up to rearrangement, or they should have the same Cayley diagram up to rearrangement. So one should not have an element. So their elements need to all be of the same orders as well. And that's often a way to spot to see if two groups are not isomorphic. I think that if you want to show that two groups are isomorphic, you probably can't just see it from like visually. You'd have to more give out like, well, they look like they're the same kind of argument. But remember that you can rearrange things in Group Explorer by rearranging by a subgroup. And that can help you explore these groups a little bit better. Okay, and then for the exploration, what I encourage you to do is take these diagrams and actually label the nodes. So choose one of them to be the identity. They're all equivalent. Really, so choose one to be the identity and then say, okay, well, if this one's the identity, then I follow a red arrow. Well, it's going to be this permutation. If I follow another red arrow, it's going to be this permutation squared. And start labeling the arrows so you can kind of see, okay, well, what permutations are occurring around one face of this or around one face of this? How do these arrangements compare? So that's just a little exploration to get you used to working with objects like that. Okay, so I hope that these problems have helped you explore permutation groups. I've been trying to keep the problems to about 10 every week, but this isn't very many problems to get you used to permutation groups. So I also encourage you to look at more problems, either from the Dana Ernst textbook or from our course textbook, to help you better understand permutation groups and isomorphisms. Really, any of the problems are appropriate, and then they go from easy to hard, so you can choose where you want to go in that spectrum. Good luck.